Welcome to a slideshow on discrete choice modeling. My name is George Boomer. Discrete choice modeling represents a major advance in tools for market planning. This presentation serves as a brief introduction to discrete choice modeling and describes one of many applications for this versatile tool. A useful starting point is to recognize situations in which DCM applies. These often arise in the form of questions posed by clients. For example, how should we price our products? How can we configure our product to compete against changing competition? What is the value of our brand name? Can we identify market segments based on customer needs? Let's talk for a moment about DCM theory and how the technique evolved into a business tool. DCM developed along two parallel paths in psychology and economics. Its roots lie in the study of how people make choices. Economists became interested in DCM because all economic transactions involve choice. The choice of whether to buy, what to buy, and when to buy. Some time ago, psychologists realized they could not observe all the factors that influence choice. Many factors were observable, but some remained elusive and perhaps random. DCM rests on what economists call random utility theory, which states that a component of choice is systematic and measurable. The remainder cannot be directly observed, but we can make some reasonable assumptions about the distribution of these unobserved factors. DCM applies when a situation is characterized by a finite, mutually exclusive, collectively exhaustive set of alternatives. If alternatives are continuous rather than finite, use regression to fit the data. If alternatives are not mutually exclusive, you can often transform the data to make them so. If the set of alternatives is not exhaustive, you'll get biased results. We now introduce an example that we will use through the rest of the presentation. Assume that a commuter has a choice of taking a car or bus to work. The utility of taking a car equals the value of observed attributes of the choice of a car, sometimes called a representative value, plus the value of unobserved attributes. Likewise, the utility of taking a bus equals the representative value of the bus choice plus the value of unobserved attributes for taking a bus. In our simple model, the value of each alternative is a function of cost and time. So for example, as the cost of taking a car goes up, perhaps through a new road toll, the value of taking a car declines. Likewise, as the time for commuting by bus decreases, perhaps due to an improved schedule, the value for taking a bus increases. Therefore, we expect the signs of our two parameters, alpha and beta, to be negative. An implication of random utility theory is that we cannot predict a consumer's behavior with certainty, but we can make probability statements about that behavior. These probability statements impose a particular form on our results. First, probabilities must range from 0 to 1. Second, the sum of probabilities for all alternatives must equal 1. You'll recognize this as standard probability theory. Here you see what are called logit equations for the probability of taking a car and the probability for taking a bus. The logit form of probability satisfies the two conditions from the previous slide, but it's mathematically easier to deal with than other distributions such as the normal distribution. Note that when v goes to minus infinity, p approaches 0. Likewise, when v approaches plus infinity, p goes to 1. Also, if we sum the p's for car and bus, we obtain 1. So the conditions in the prior slide are satisfied. Now let's add another requirement to our list. The probability function must be S-shaped. The logit equation that we saw on an earlier slide generates an S-shaped curve. This curve has a number of attractive properties. For example, if commuting by car is very expensive, then the point on the curve will be towards the right, and a slight reduction in cost will have a negligible impact on the probability of taking a car. Similarly, if taking a car costs next to nothing, then the point will be on the left side of the curve, and a slight increase in the cost will not affect probability significantly. The greatest impact of a change in price takes place when the probability is close to 0.5. This, interestingly enough, contrasts sharply with conjoint analysis, which assumes the relationship that you see here is a straight line. Now we add another requirement to the list that we've been developing for choice probabilities. That requirement is, if we add an alternative, the probability for other alternatives drops. Our logit formulation supports this property nicely. If we add an alternative for rail, you can see from the above example that the probability for car decreases. Likewise, we can conduct the same analysis for bus, and the probability for bus would decrease. We return to our equation for representative value. As you can see, the value for a particular mode of transportation is equal to alpha times the cost of that mode plus beta times the travel time for that mode. We can estimate the values of alpha and beta using a statistical technique known as multinomial logit. When we do this, we obtain the value of minus 0.24 for alpha and minus 1.20 for beta. Now there's an interesting interpretation to these coefficients, and that is this. At the margin, a typical commuter would value his or her time by the ratio of these two, the ratio of the time coefficient to the cost coefficient. In other words, minus 1.2 divided by 0.24, or about 5 pounds per hour. This turns out to be a fairly reasonable amount. Having estimated values for alpha and beta, we now turn to socioeconomic variables. So far, we've assumed that our population consists of homogeneous commuters who value car and bus alternatives in predictable ways. We now relax that assumption and explore whether differences among commuters affect the valuation each one places on cost and time. One way to do this is to add socioeconomic variables to our equation for representative value. We've done that in the above equation, in which we explore the possibility that after allowing for differences in cost and time, people with higher incomes tend to commute by car more often than people with lower incomes. We can test whether this assumption holds by estimating a value for gamma and seeing whether it is significantly different from 0. If this is true, our specification works. If not, we must reject it. We can consider other ways for incorporating income into our equations for a representative value. Let's say that we think the importance of time is proportional to a person's income, so that as a person's income goes up, the value of time goes up. We can do this by choosing the specification that we see at the bottom of the slide, in which the representative value for car is equal to alpha times the cost of car plus delta times income times the travel time by car. We can now estimate the values for alpha and delta and see whether or not the estimate for delta is significantly different from 0. As we've just seen, the logit specification has some nice features, but it also has some peculiarities that we have to bear in mind when applying it. The most critical of these is what's called the assumption of independence from relative alternatives, also known as IIA. This means that the odds ratio of any two alternatives, such as car and bus, don't depend upon the presence of any third alternative, such as rail. In many instances, this reflects the way the world works, and it's not a problem. But in other cases, it poses difficulties that we have to address. The best way to illustrate problems that arise from the IIA assumption is to use an example. One that's commonly employed is something called the red bus, blue bus problem. Suppose there's one bus on the route, a blue bus, and suppose for now that the value of taking a car just equals the value of taking a bus. Then the probability of commuting by car equals 50%, the same as the probability for commuting by bus. Now let's say that the bus line adds a red bus that's identical in all respects to the blue bus except for color. If these buses are truly identical, and we assume riders don't really care about bus color, then we expect the probabilities of taking them to be the same. Another way of stating this is that the ratio of the probabilities equals 1. However, because of IIA, logit predicts that the probabilities of taking the red bus, blue bus, and the car are all equal. This happens because the ratio of car to blue bus is 1, the ratio of car to red bus is 1, and the ratio of blue bus to red bus is 1. So according to logit, the probability of each must be 1/3. Now common sense tells us this is wrong. In reality, we expect the probability of choosing car to remain at 1/2, the probability of choosing a blue bus to be 1/4, and the probability of choosing a red bus to be 1/4. We can illustrate this problem graphically. The red bus blue bus problem arises when choices are nested. At one level, the commuter chooses between the car and bus alternatives. Within the bus alternatives, he or she then chooses red or blue. This doesn't necessarily imply that the choices are made at separate times. They might be made all at once, but the components of the choice behave as you see in this illustration. So how do we correct for IIA violations, such as the one illustrated by the red bus blue bus problem? Mathematically, we can do that by adding the natural log of 1/2 to the representative values for the bus alternatives. When we do this and revise our calculations, as you can see in the slide, we arrive at the correct probabilities. How do we know to pick the log of 1/2 as our correction factor? Clearly, it's the right factor to use in this situation, but would it apply in other situations? The answer is that each situation has its own unique correction factor that must be estimated statistically. There are some fairly advanced statistical techniques that allow us to find out what this value is. Other statistical techniques let us test for the presence of IIA violations. A number of approaches exist for estimating nested models, such as the one we just saw. One approach involves estimating separate linked models for the upper and lower nests. Another approach estimates them jointly. Still others let us investigate complex nesting schemes, such as more than 2 nests or overlapping nests. Having talked for a short while about logit theory, we now turn to the problem of collecting data. There are basically 2 ways to do this. The first involves going out into the world and looking at the choices people have actually made, such as observing which cars or clothes they have bought. In this case, we observed what is called their revealed preference. This would be analogous to going out and observing whether people actually take cars or buses to work. By contrast, we can present people with hypothetical choices and ask them to pick one or more. Because this is usually done in an artificial setting, we observe their stated preferences rather than actual behavior. This would be equivalent to surveying people and asking them, if you had the alternative to take a car versus bus, which would you choose? Each of these 2 approaches has its advantages and disadvantages, which we list in detail here. Revealed preference observations tend to be more reliable than stated preference observations, because revealed preference is based upon what people really do rather than what they say they will do. On the other hand, companies often want to test new products that don't yet exist in the real world, so they must rely on stated preference studies. Also, in the real world, many product attributes such as wheelbase and trunk space are highly correlated. If companies want to investigate how consumers separately value each of these components, then they're forced to use stated preferences to avoid confounded results. Strengths of the 2 techniques can be leveraged by using hybrid approaches. As an example, you can conduct a stated preference study under controlled conditions, then go to the field to collect revealed preference data. The new data can then be used to calibrate the results from the stated preference study. As we just said, one advantage of stated preference studies is that you can construct choice sets in which product attributes are uncorrelated. An entire branch of statistics deals with how to construct complex experimental designs, and that branch of statistics is beyond the scope of this presentation. We'll say only that many sophisticated techniques exist for constructing choice sets, such as the one that you see in this slide. In constructing experimental designs, researchers have 3 considerations. The first is called level balance. This means that the frequency with which options appear should be the same in each choice set. In other words, if you're considering 2 alternatives, rental, purchase, then the option rental should appear in half the choice sets and purchase should appear in half the choice sets. Likewise, if you are considering 3 levels for an alternative, then each of those should appear in roughly 1/3 of the choice sets. A second consideration is what's called uncorrelated attributes. We've already talked about this before. This says that one choice should not be correlated with others across the choice set. In other words, if you're considering looking at monthly charges versus device costs, then the values that you pick for monthly charge should be uncorrelated with the values that you pick for device costs. The third consideration is equivalent utilities. This means that one choice should not dominate others in a set, and likewise, a choice should not be such a bad choice that no one chooses it. You want to try to set up the choices so that there's a roughly equal opportunity for people to pick any of the choices in a set. Once we collect the data and estimate the parameters in our model, the next task is to produce forecasts. The problem with doing this is that we have measured choice at the level of the individual, yet the probability for choosing car, to use our example, differs for each person. So how do we address this? There are two solutions. The first is to use what's called market segmentation. That means we partition the population into an exhaustive set of segments. One segment for each of the social demographic variables that we've used to estimate our model. Then we compute the frequencies, the probability for car, for each segment. We sum all the segments together, and that gives us an estimate of the total population. The second approach is to use what's called sample enumeration. That involves representing the population through sampling. When we do that, we calculate the probabilities for each individual and then multiply the probabilities times population weights. We've taken the market segmentation approach and used it to construct a spreadsheet-based simulator. The above example that you see in the slide represents such a simulator for personal communication services. The user can configure a marketplace of up to 8 products, only 5 of which are shown in the slide. In the green areas, the user can specify products in detail, including pricing, rent versus purchase in this case, brand, promotion, features, and other attributes that happen to be associated with the product. The simulator then calculates purchase probabilities and therefore potential market share for each product. By changing assumptions for price or features, the user immediately sees the impact on potential market size. Here are some examples of pricing simulations that can be done with the simulator that we saw in the previous slide. We can add cost structures for the handset and for each of the features in the PCS services we're going to examine. The model will then solve for potential profits, or more specifically contribution margin, in addition to potential revenue. The user can then adjust product assumptions and find the combination of pricing, branding, and features that will stage the biggest win in the marketplace. Incidentally, looking at this chart, you can see the difficulty in setting the appropriate price. In this scenario, the price that optimizes profits sacrifices market share. A company facing this situation must choose between a price that generates good profits in the short run, only to surrender market share to the competition in the long run. Addressing this question would involve estimating switching costs, evaluating the effects of churn, and assessing the impact of aftermarket service. We have seen how discrete choice modeling can improve a firm's ability to price and position its products in a competitive marketplace. At a broader level, DCM is changing some long-held marketing concepts. Many firms engage in a debate concerning whether to boost profit margins or increase volume. We now know that this is the wrong debate. In each competitive situation, there is usually one product price that generates maximum profits. We've also found that patterns describing customer choice can be extremely complex. Certain features can appeal to some market segments, but not others. Demand for some features is occasionally linked to demand for others. Finally, the complexity and dynamism of market choices makes it very difficult to design effective strategies without a simulation tool, such as the one that we have shown you. We've seen how discrete choice modeling adds a new dimension to market research. It can provide insights not available through other techniques, and it can help companies fine-tune market strategy to an unprecedented degree. Thank you for listening to our presentation.